Good to see you all here, virtually at least. This evening we're going to talk about cloud design patterns. This is a talk I've given a couple of times before. This is my first time giving it without an in-person audience, so that'll be a little bit different. Like Sam said, feel free to raise your hand or stop, or just unmute yourself and ask a question as we go. We have a pretty small, intimate group here, so it shouldn't be a problem, and it'll be probably more interesting if it's more of a discussion than if it's just me talking for a long time. If you are looking for other resources after this evening, you can listen to my podcast on weeklydevtips.com. I don't have a lot of stuff there that's cloud specific, but I have a lot of just general dev tips there. And each episode is only about 5 or 10 minutes and just talks about one quick tip. So it's easy to fit that in with any other podcast you might listen to. I've started a developer career mentoring program at devbetter.com. So if that sounds interesting, go check that out. And I have a couple of ebooks that I've written for Microsoft that are available for free. One is the architecture ebook, which has got a really short name of Architecting Modern Web Applications with ASP.NET Core and Microsoft Azure. And that's been out for a while, and it goes along with the eShop on Web sample app. And then the other one is newer. It's still in preview, although it's been mostly done for almost a year now. Microsoft just hasn't taken the preview label off of it yet. But it's this Architecting Cloud Native Apps for Azure, which I wrote with Rob Vetter. Okay, so to get started, what I like to do is kind of reset and kind of take a history lesson, as it were, on how we got to the cloud, right? And like, where did we start before the cloud? And a lot of us have been there, and we have the battle scars to show it. But for newer developers, this might be interesting in terms of where we came from. And I do think it kind of informs the decisions about the way we architect things in the cloud and some of the patterns that we use. So we're going to start by taking a quick trip back to the beginning of what today we call the web. So we're going to go way back, but not that far. We'll go back just about 20 years ago. And so about 20 years ago, this was a Compaq Alpha server. In fact, today it would still be a Compaq Alpha server, and it would host your web server as well as your database potentially on the same machine. And it had a bunch of little peripherals and devices and things that you'll probably recognize. You could open it up, and it had a whole bunch of bays for hard drives that you could throw in here. And of course, SSDs weren't a thing, so these would be like ginormous spinning Rust drives. And anything you needed would be on this box. This is where all the web server logic lived. It's also where all the data might live. And you would just talk to this thing over the network to do your web development. Now, what is this thing right here, right? That doesn't look like a mini DVD drive. That is actually a save icon dispenser. So if you've ever seen a save icon, that little blue thing, this is where those come from. They would spit those things out. It's actually a little 3.5-inch floppy drive. And back in the day, that 3.5-inch floppy drive would be the A drive on your computer. So if you've ever wondered why like your hard drive generally now starts at C, that's because A and B were typically reserved for these floppy drives. And interestingly, you could actually install whole operating systems off of just like 3 of these 1.5 meg floppy drives way back in the day. Now Windows, you have to have like 20 gigabytes just to install Windows. So obviously that was a long time ago and things were a little smaller then. Now, if you use this architecture, typically you would just have one web server to rule them all. And so it did all the work. And you would have some client machine, which would be some, ginormous Packard Bell or something computer, and it would be running NCSA Mosaic as its browser, and it would make a request to the server. And on the server, you would have the application and whatever data it needed, and it would process whatever it needed to do, and then it would return back some response in HTML. Right? Angle brackets would go back and forth. And of course, you would have a webmaster running all this. And the webmaster was like the original full stack developer because they had to do all this stuff. Okay, so let's break this down a little bit and see what actually happens when that client makes that server request. So looking at this, what you might remember is that this was the 90s. And so smartphones weren't really a thing. Let me see if I can get this out of my way. I'm trying to see stuff on my other screen. GoToMeeting wants to be in the way. All right, there we go. And so you would have computers involved in both ends of this, obviously, but you wouldn't typically have, your mobile device. Like today, well over half of web traffic comes from phones and mobile devices. Back in the 90s, web traffic involved phones, but not really in the same way. So desktop computers would look something like this ginormous Packard Bell. They would have these huge CRT monitors. Flat screen monitors weren't really a thing. Certainly no LCDs. This example here, this Packard Bell, I had one of those. They were awful. You would never want a Packard Bell. Fortunately, they went out of business. And then you would get on the internet using one of these CDs. And so, anybody remember these from AOL? You can use them as coasters now today. So back in the 90s, AOL just carpet bombed the country with these CDs. They were literally everywhere. And so whenever you needed to get online, you would just walk outside, pick one of these up off your front yard, and put it in your computer. And that's how you'd get on the internet. You'd sign up with an AOL account, and then you'd use your modem, which was probably in your computer, and it would talk over the phone, but not your cell phone. Now we're talking about your actual house phone, which might have looked like this. All right, this is the old rotary style phone. Every time you wanted to dial a number, you had to wait for it to go click, 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 click all the way back. And your modem would dial on your phone line, and it would make a horrible sound that I don't think I have my sound shared, so you won't be able to hear it. But the rotary phone, interestingly, is like the inspiration for the original iPod, which many of you probably have forgotten about by now, but it would have this rotary UI that you would use. And so when you would click with the modem, it would make this long sound, and you can't hear it, but it's playing for me right now, and it would dial the number, and then the modems would talk to each other, and there'd be this handshake, and there would be this like bum sound as they communicated with one another. And so that would let you get to the computer, and then you were online at that point. Fortunately, you didn't have to do this for every web request. You only had to do the connection one time to get on the internet. But while you were online, your phone couldn't be used. It was busy with the internet. Now the server would actually do its job, right? It would process your request. It would run some VB script or some Perl or something like that, and it would start sending the response back. And servers were not very fast, so this would take some time. And this was actually like how fast pages might render. And this was the original Amazon.com homepage, or one of them from back in the 90s, right? With their really cool logo there that kind of looks like a river, like the Amazon. All right, so that's the way things worked back in the day. And so this architecture is basically the simplest architecture you can get. You've got everything on one box, right? So we can look at these different variations of architectures, which we're going to see in the course of this presentation. We can evaluate them based on these types of metrics, right? These types of considerations. And so we're going to drill into each of these. We're going to look at availability, how we deal with data, the design and implementation of this pattern. What does it do in terms of messaging? How do you manage the servers and the architecture overall? What performance and scalability impacts does it have? How resilient is it? How good is it at staying up in the face of updates or crashes or hardware failures? And then how secure is it? So we're going to talk about web app considerations and challenges, and specifically we're going to talk about cloud-hosted web app considerations. And so the very first one is availability that we want to look at. And this just represents the proportion of the time that the system is functional and working. Usually you measure this in terms of uptime and as a percentage. So this can be impacted by system errors, infrastructure problems, attacks, system load, all kinds of things can affect your availability, including scheduled maintenance. But it's basically just how often are you up? What is that as a percentage? For reference, if you have 99.99% uptime, so 4 nines, that equals 1 minute of downtime per week. As you add more nines, it gets more difficult to maintain that level of availability. With each additional 9 being basically 10 times more uptime. And so that much less ability to be down ever. All right. Data management is the next one. And so with data management, this is a key element for cloud applications, and it influences most of the other quality attributes, right? How you deal with data is going to affect your scalability, your security, your uptime. All those things typically will be dependent on this. And so there's many more options in the cloud than there are in a traditional single database application. You have options for distributed data. You have to deal with consistency. You have to worry about how synchronization is going to work. And so all those things come into play when we start evaluating the data management side of any particular architecture. Then you have design and implementation. And this is not so much the UX as the design of the entire architecture of your system. And so here, consistency is key because you really want to be able to treat your servers like cattle instead of like pets. You want to be able to create them and take them down anytime you need to. You don't want to give them names and get emotionally attached. You want to just be able to treat them like just arbitrary resources that you're not worried about. So you want to think about factors like how easy is it to maintain the architecture? What is the administration like? How can you develop against it? What are the diagnostics of it? Like how easy is it to determine what goes wrong? How much does it cost is also obviously a key factor. So these are all things to think about with this design. Then you have messaging. As soon as you have more than one server, you have to have some way for those servers to communicate. And so you have to think about how do subsystems talk to one another. The distributed nature of cloud applications requires more thinking about and more messaging infrastructure to connect components and services, ideally in a loosely coupled manner so you can maximize scalability and availability. You have to think about that more in a cloud architecture than you do in a traditional client server system. Asynchronous messaging is widely used and can provide many benefits, but it has challenges as well. So you have to think about, are we going to do direct synchronous calls? Are we going to use asynchronous messaging? Each one of these has its own challenges. All right, so then you have management and monitoring. If you're using a platform as a service or PaaS system, you don't necessarily have direct server access, right? That comes along with the idea that these aren't servers that we actually know about and remote into and maintain manually. These are just resources that are being used. So if you can't just log into it and see what's going on, how do you diagnose when a problem occurs? How do you check to see that everything is going okay, that the performance is adequate, that errors are not queuing up? So that's all concerns that you have once you start moving more and more to a cloud and PaaS design. Cloud resources are more like cattle herds than pets, like I already mentioned. So this becomes more and more true as you move away from physical servers toward virtual servers, toward containers, and even just platform as a service PaaS offerings. Okay, so then that brings us to performance and scalability. A lot of people think these are kind of the same thing, but they're not. They're related, but they are different. So performance and scalability generally wants to know like how responsive is the system to requests, that's performance, and then how does this responsiveness change with increased load, that's scalability. So you might have a system that performs relatively poorly, right? Every request that comes in, it takes 3 seconds to process, but it can do that for 1 user or a billion users, no matter what. It's got 3-second time to process that request. It is really scalable. Right, that's perfect scalability if it has no change in response time, no matter how much load there is. Most of the time, as you add additional load, at some point, performance will exceed an acceptable threshold, right? And so what you would like is for scalability to be as close to linear, as close to flat as possible. And if you do need more scalability, you can just add additional resources to get it. There's generally 2 ways to scale. One is scaling up, which just means put more resources on the boxes you already have, add more CPU, add more memory, put in faster network cards, faster hard drives. But eventually you reach a limit there where you've bought the fastest of everything there is on the market and your machine is maxed out. At that point, the only option you have is scaling out. And scaling out is where you're just going to add more machines, right? And there's no theoretical limit to how many more machines you can add. Especially since those machines might not even be real machines. They could just be virtual machines at that point. And so what your goal is with performance and scalability is if you need a lot of scalability, you want to be able to add additional machines that aren't necessarily top of the line machines, because that's not price effective generally, but you want to be able to use a whole lot of relatively cheap instances and scale those up and down as needed. The other nice thing about scaling out is that you can respond to demand elastically in the cloud. And so when you see a spike or a surge in traffic, either one that you know is coming because it's Black Friday, or the open enrollment for your insurance just opened up this morning, right? That's coming. Or it could just be a spike that you didn't know about because some tweet went viral and a whole bunch of people are buying your product now. Either way, you want this to be able to just automatically increase the number of instances that are serving your demand, and then when that peak diminishes, just automatically scale back down to whatever your residual amount of hosting capacity might be. All right, then we have resiliency. If the system has problems, can it gracefully and hopefully automatically recover from those? You want to be able to detect failures and then recover automatically. no matter what those might be, whether that's a hardware failure or a critical failure in your application or even a hack of some sort. You want your system to be able to come back online as gracefully as possible. And then finally, security. Security is super important these days. It really always was, but we see more and more public and widespread attacks occurring. We have attacks occurring not just on big obvious targets like banks, but on much smaller targets as well. So local towns are getting hacked, and then they're having all of their servers encrypted, where now ransomware is being applied, and unless they pay $1 million, they won't get any of their data back. These types of attacks are occurring. Small websites get hacked so that the user list in there can get pulled out. And since users aren't very good about changing their passwords between different applications, all those emails and passwords in some little server that nobody cares about that's just got like pictures of cats, now that can be weaponized and used to get into people's eBay accounts or Chase Bank accounts or whatever, because users are lazy and they happen to use the same passwords in two different websites. So you want to be able to protect from attacks. You want to guard sensitive data. You want to be able to partition sensitive data from not so sensitive data. You want to be able to restrict access to approved users, right? And so these are things that we want to make sure of in terms of security for our system. All right, so let's back up to our one machine example. Right, this is a standard, basically client-server architecture where the client makes a request to the server does all the things, and it returns back. So if we look at our report card now, uptime, not so good. It's got a single point of failure. Anything we have to change on that server is going to take it down. Right? If we have to replace a hard drive, we have to upgrade the database, we have to patch the OS, any of that stuff, server's going down, users can't access the system at that point. Data is not bad. There's only one data store. It's all in one place. It's easy to update. It's easy to make backups of. So that's not bad. The design is about as simple as it gets. So we'll give that a happy face. Messaging too, everything is in proc. We don't have to worry about any out of process calls. So everything is fast and reliable. If something's going to fail, you're going to know about it immediately. And you're not going to have to worry about whether or not it maybe at some point, comes through. Management is also about as simple as it gets. There's just one machine. You can do anything you want on there. Performance and scalability, this is good, but also bad, right? Performance is good because all of your requests processes are happening in memory in that one box, right? So there's no out of process things that are going to take extra time. Every time you have a web request you make to a server, and from there, it makes an HTTP call to some other place, and then it makes a database call, and then it makes another database call, and then it makes another database call, because that's how most data-driven apps work, is they make a lot of database calls. Every one of those adds up in terms of how much response time that page is ultimately going to have to return back, or that API call, or whatever it might be. By keeping everything on one box, you minimize all of that latency of going over the wire to talk to other things. So performance is really good here. Scalability, though, is not good at all. So the only thing we can do on this is throw more hardware at it, and eventually that's going to not be enough. So scalability is not so great. Resiliency, it's hard to say. There's not a lot of external management of the machine, probably. So if it fails, somebody probably has to, remote into it, or even just walk up to it if it's sitting in your data center and reboot it or diagnose it or whatever it needs to be. And security can be good, right? There's not a whole lot to it. There's only one thing. So if you secure that one thing, you're in good shape. But also it's bad because there's no partitioning. So if someone gets in, once they pwn that box, they own everything probably. Okay? So that's kind of where we are with, before we get to the cloud, here's my one box that's hosting everything. And eventually that's not going to cut it. So demand grows. And remember when we used to do stuff like this and we didn't have to have masks and social distancing? Like, I looked at this slide before the talk tonight and I was like, wow, we would never do that now. That's crazy. Those people don't have masks on. All right, so current assessment, as we're scaling out, we start to hit limits, right? So our vertical scaling gets maxed out. Performance is suffering when the site is busy. So there's a couple things we can do real quick. And I'm sure the things that you're immediately jumping to and are probably saying, well, I would never even started like this, right? And the first one is, why don't we move the database to another server? And that's an obvious one, right? And also your DBA is also generally not your webmaster if you have a DBA. And so the DBA really likes to own that database server and really restrict how the web developers get to it. So this has some nice security advantages as well if you move the database to another server. And oftentimes the company is more than willing to throw a lot of resources at the database server because it's probably shared by a lot of different applications and a lot of different departments. Whereas the web server, they tend to be less excited about putting a lot of resources into. All right, so with this now, we've moved up to two machines. We have a web server and we have a database server, and they talk to each other. And this is probably still today the most common pre-cloud architecture for web apps, right? Is a web server with a database server. All right, now parts of the app might still be slow as demand continues to grow. And so what can we do about this? Well, let's say that we've maxed out our vertical scaling. So either we can't add any more hardware or we don't have any budget to do so. The next thing is I want to look at the data and make sure the data is indexed well and has all the things it needs to perform quickly. So let's say we've done that, right? The data has been optimized. There are the appropriate indexes. We've analyzed it to make sure of that. But some queries just hammer the database, and these take time. And they don't just impact those pages or those web requests, but they impact the whole database, and they're slowing down other requests. So what can we do to address this? And so that brings us to our first cloud pattern, which you can actually use outside of the cloud. Most of these patterns aren't cloud specific, but it's very, very commonly used in the cloud, and that is the cache aside pattern. And so there are dedicated cache products that you can just install in the cloud and use, and they will implement this pattern directly. If you're not using one of those products, you want to implement it yourself, perhaps using an in-memory cache, it's pretty easy to do that as well. There's these two sub-patterns to this, two strategies. There's read-through and write-through caching. And so read-through caching looks like this. When a request comes in, the first thing that the system does is check to see whether that thing that they're looking for is in the cache. And if it is, it will just return it. But if it's not, then it will fetch it from the actual data store and store it in the cache and then return it. And so the user doesn't know the difference, right? The end client has no idea whether they got the data from the cache or they got the data from the data store. They just know they got the data. And when they get it from the cache, they get it a lot faster, typically. All right, so then on the flip side of this is you're going to want to have a write-through strategy. And a write-through strategy says when someone updates a record, we need to update the data store and put that into the actual database, but we would also really like to make sure that the cache gets updated as well, because otherwise the cache will be out of sync and the user will be upset that they just updated something on their system, and then the next page that returns back and they see, it reads it from the cache and they don't see their change, right? That causes a lot of user frustration. Another option that is sometimes a choice is to just use a very short cache duration, like really short, like less than a second, right? If you have a really busy application and it's getting hammered with requests, 10 requests per second, 50 requests per second, 100 requests per second, then if you just give it like a 500 millisecond or 1 second cache, that's going to be enough that any of these common caches that are common queries that are being made that are being cached are going to get updated all the time, but they're still going to dramatically reduce the load on your database. If you have a page that's loading, or every page in your system is loading, and the navigation is being read from a database table, and you read that every single page request, if you cache that for 1 second, then instead of, if your web traffic is 50 requests per second, instead of 50 queries per second hitting the database, now you've got 1 request per second, right? It's dramatically better. So don't discount the idea of just throwing a cache on there and giving a really short duration to it. It works well in the cases where you have a lot of traffic for that same request. Okay, so if you want to add simple memory caching to our architecture, we would just put this cache on the web server, and now it's going to be able to check and see if data is in the cache before it actually hits the database server. So that brings us to the only two hard things in computer science. The first one is cache invalidation. Figuring out how to do cache invalidation right is generally hard because there's so many variables in terms of how you can do it. So if you keep it simple, then it's not too bad. But if you start making it more complicated, it will definitely get harder. The second one is naming things. And the third one is off by one errors, is also a really common hard problem in computer science that you have to watch out for. Now, speaking of naming things, you want to use a standard way to generate the cache keys that you're using for given scenarios. You want to avoid hard coding those cache keys as string literals inside your actual source code, like you're going to see in literally every single article on caching that you'll ever read. because that works great for demos, but that's not what you want to use for your actual production code. Many caching patterns will require access to those same keys from different parts of the application. If you're using a read through and a write through strategy, then you need to know what that key is for that resource, both when you're reading and when you're writing. And if the only place that you've stored that is in a string literal in the read method, then you're going to have to copy paste that into the write method. And obviously things are going to go badly when those get out of sync. The specification pattern, which I don't have time to talk about here tonight, is a good pattern to use to generate your keys. It's demonstrated in the eShop on Web sample app that you can look for on GitHub. I also have a NuGet package called ardalis.specification that you can use to get started with this pattern. Specification pattern basically describes a query as a class. And so in that class, you're going to have everything you need to know about that query. And so it's a perfect place for you to also generate the cache key for that query. Okay, so now we've introduced a cache. So now we have some new problems, right? Our performance is generally much better. Some users are still going to complain about delays when we hit those really tough queries and the data is not in the cache. The other thing that's a problem now is that we have to keep the cache up to date, right? Because of how we implement the cache, if we aren't doing that write through strategy effectively, there is going to be some period of time before those caches expire when customers may see stale data. Also, now that we've added this other moving part into our architecture, we have to have new monitoring for the cache. We have to make sure we're checking to see if the cache is performing, what is its hit ratio, are we running out of memory, things like that. So we have to have new tools to clear or update the cache. The easiest way to clear the cache in ASP.NET traditionally is to go into your server, go into web config, hit space, and then Control S, and it will save web config and it will tear down the whole application and restart it all. That's using a really big hammer to do this simple task of just restarting the cache. You would like to have better tools than that. Unfortunately, depending on what type of caching you're using, there may or may not be good tools built in. So you may have to actually write those tools and roll them out yourself. Okay, so that's a lot of red stuff, right? But it's okay. Things are bad. We're all fine. Everything's fine now. We're good. So we're going to fix that in a minute. All right, so demand is going to continue to grow. At this point, it's time to scale out. So far, we've basically just kept everything on that one web server, but now we're going to introduce a load balancer and a simple web farm. So looking at this diagram here, you can see that the client machine is now making requests, but instead of going directly to the IP address of a web server, they're going to the IP address of a router, a load balancer network device. And so this load balancer has some logic that it uses to determine which web server it wants to send traffic to. And in this case, we only have 2, but there could be n number of web servers. There could be many more. And the most common one is that it just uses a round robin approach where every request goes to A and then B and then A and then B, or it randomly picks one or whatever. More sophisticated load balancers might have more sophisticated strategies where they'll check and see which web server is not too busy and they'll send more traffic to that one. You can also get into things like sticky sessions where the load balancer can check and see if the last time you made a request it went to server A, then okay, this request we're going to send to server A also. But we're not going to assume that we have that on this load balancer right now. So in this example here, when updates happen to the database, it's possible for those 2 different in-memory caches to get out of sync. Even if you're using a write-through cache strategy, web server A might go ahead and update its cache, but web server B is out of the loop and has no idea that this has even happened. And so its cache might still reflect the previous value prior to the update. And so request 1 might come in here, request 2 might come in there. And sometimes we get problems with the caches being out of sync. Okay, so performance is even better now with a web farm, and it's easy for us to scale it out further by just adding more servers. Some users are still going to complain about cache misses. We'll try and come up with a way to fix that at some point. And we found that keeping multiple caches up to date is a big challenge in this model because they don't know anything about each other. The best thing that we can do is either put in sticky sessions, which has scalability issues, or use really short cache durations so that by the time the next request comes in to a different server, that cache has already expired. But really short cache durations, while I'm a big fan, really only work for data that's being hit all the time. Data that's being that's expensive to create and doesn't get accessed very often. You might still want to cache it, but you're not going to want to blow away that cache all the time. Okay. We need new monitoring and tools now to manage this load balancer. We have more servers we have to manage. We have to hire more network administrators to deal with this, or they have to work more hours. On the plus side, though, on availability, we can now update web servers without taking down the whole system, because we can just pull one of them out, tell the load balancer not to send it any traffic, make whatever upgrades to it, whether we're updating the application or patching the OS, whatever it might be, and then put it back in and then repeat that process for each other server until they're all updated. All right, now at this point, you're probably reaching the limits of what you want to do in your own data center, whether it's yours or hosted at some colo center. So it's time to actually embrace the cloud. And so it doesn't really matter whether you're using Azure or AWS. Pretty much these patterns we're going to show all work with all the different cloud providers, except perhaps the Black Hat cloud provider in XKCD. So I'll let you guys check this for a second. I'll see if there's anybody's got any questions, and I'll grab a quick drink of water. Can I see questions somewhere here? Oh, there's the chat. All right. Cup holder, tech support joke. Yay, people like my joke. Todd asked why, but I didn't see it, and I think he left. Sorry, Todd. And just for kicks, it's on an old box. All right, that was a while ago, though. Nobody's asked anything in 20 minutes. Awesome. You guys are all doing other things. Todd's still here. Hey, Todd. Thanks. You said why, but I didn't know what your context was. If you want to tell me why what, I'll try and answer. I think that was way back in the 1990s portion. Why Sam still had the 5 1/4 inch drive? They're going to be worth something someday. That was back when floppies were floppy, right? Once they went to the 3.5, they stopped being floppy. They hid the floppiness inside of the rigid exterior. All right, let's get back into it. Simple cloud architecture. Now we're going to use different icons. Fancy. Right, these are all the latest Azure icons. And so here we've got the Azure load balancer. We got a bunch of app service instances. These are no longer servers, right? These are just app services. This is platform as a service. I'm just going to deploy my code to Azure, and it's going to figure out where to run it and how to run it. It's going to be totally virtualized. I don't even necessarily know or care what operating system these things are running on, because I can be using .NET Core, and it runs whether it's on Linux or Windows or what have you. Now, one thing I can do with these app services, I can still just use an in-memory cache, right? That's just built into the .NET framework, and I can easily just use that, or I can even write my own. But we also have some nice built-in services in Azure, like the Azure Cache Redis instances that we can use. The benefit of using a shared cache like this Redis cache is that now we don't have to worry about cache synchronization. So it's not quite as performant because there is another network hop to get to the data, but it has much better scalability, and you don't have to worry about the cache synchronization. So those are both good things. And then you have your SQL database on the back end. So with this architecture, what do we have? We have better scalability. Our cache synchronization is much easier. We have no servers to manage. We have all the monitoring tools built into the platform, and our web instances are easily managed without downtime. We can also do elastic scale. We can just go into our Azure dashboard and say, you know what, when things are just normal, I want to have 2 of these web instances, but if their CPU exceeds 60%, I want you to add more, and I want you to keep adding more up to a maximum of 10 or whatever. And so we've got some pretty good options here for how we want to manage things in the cloud. Much better ratio of happy faces to sad faces. But what happens when we want to build more of these apps? Because we're at large companies or even small companies where we don't just ship one application, right? We have a lot of different applications that we have to support and maintain. And so when we want to take more applications, we need to take these app instances and replicate that primarily, right? The load balancer, the database, those things are probably going to be shared, or they're at least going to be fairly consistent in how they're deployed. And hopefully we have some way of scripting the resources that we need in Azure. But the app service instances, that's mostly what the developers care about, is how those things are set up and how they interact with one another and with their resources. So let's just drill into this part of it and see, okay, what happens when I have several of these? I've got app A in blue, app B in green, app C in orange. They're going to talk to those shared backend resources. All right, so I can deploy all these things out. Hopefully I'm being smart about how I'm using tags and resource groups and things like that in Azure to organize these things. But now I've got these applications and everything's great. They're all getting all the benefits of the cloud. Woohoo! It's all roses, except a couple small things. All right, we have vendor lock-in because we are using app services. So that means if we decide that Azure is not the right place anymore because Microsoft just tripled their prices or whatever, and we want to go to Amazon or Google or whatever, it's going to be tougher, right? Because we are locked into using that app service model. If we are using that shared database, that's going to hurt our availability because even if that database is just down for maintenance, infrequently, every time it's down, all the apps are down. We have shared resources also limiting our developer agility, which impacts our design. So if we're only literally using one database on that database server, which is not that unusual, developers can't just suddenly decide that they want to refactor how the tables look, right? If you want to rename a table or rename a column in your app, you should be able to do that. But as soon as you're doing it on a shared database that several other apps are talking to, you're going to get hammered real fast when every other app is down because you decided to rename a column. And so what that means is you end up with these common tables that every application uses, and each one needs something else. And so at the end of the table schema, you've got like a whole bunch of extra columns that are all nullables that somebody's thrown on the end, because that you can do without breaking things. And over time, that just adds technical debt to the whole system. Nobody can actually change the system without breaking everybody else, and so the system doesn't adapt with future needs. So we'll address some of these in a minute, but first, let's talk about another pattern that we're going to need, and that has to do with auth. Right? We haven't talked about security too much since we jumped through a few different iterations up into the cloud. How are we going to do authentication and identity services in these applications? So these apps typically require, or you'd really like to have, single sign-on because your users, whether they're your third-party customers or they're your own business users, they're not going to want to log in differently for every different app that you deploy. So they're going to want to have single sign-on. Obviously, you need to have security. You want to protect things from unauthorized use. You want to make sure that different users have different levels of privileges. And let's assume that all this was done before this, right? And so when I've been evaluating these architectures, this was just something that was part of it, and we could expect that it was working. But if you're not careful, it starts to look like this, where there's a lot identity and tables and data inside the shared database. You can use something like ASP.NET Core membership providers, or more recently, ASP.NET or ASP.NET Core identity providers. And if you do, then you can easily scaffold out login pages for that app and that app and that app. And now every app gets a login screen. You get a login screen, and you get a login screen, and you get a login screen, and you get to maintain all those different login screens. And it's just a real pain that gets worse over time as you add additional applications. And so the next cloud pattern is this federated identity pattern. And the way this works is the user goes to make a request to an application. The application checks to see if they have a token saying that they should have access. If they don't, they're going to get redirected to an identity provider, this token service. That token service is going to ask the user to provide their credentials. So they're going to log in. They're going to give their login, their password, whatever. But they're not logging into the app, right? They're logging in to this separate identity service. Once they have done that, then that identity service is going to issue the end user a token of some sort, which they will keep and present on future requests, either as a cookie or as a header in an API. And then they will go back to the service they were originally trying to use. They will present that token or cookie, and they will be granted access because now they've been given access. Usually this uses OpenID Connect or similar protocols. The identity provider in this case could often be using a tool like Identity Server. There's also third-party tools like Auth0. What's the other one? There's another one I can't remember the name of. That are out there that you can hook into as well and just kind of outsource your authentication. Azure also has some support for this too. If you want to use like Azure AD, you can certainly integrate directly with Azure. But if you're trying to use third-party customers, you're not going to want them to be using your AD. So you're going to want to have some other way to integrate with them. A not unusual scenario that I see with my customers is they want internal users to be able to log in with Azure AD or their corporate AD, Active Directory. But external customers, they want to be able to log in with whatever account they registered with, right? An email and a password or a username and a password. And so they want both. And so in that case, that's where this federated security provider makes a lot of sense because it can do both, right? You can have as many different ways to do auth that you want plugged into this identity provider. And you can say, okay, I want them to be able to log in, and they can log in using my Azure AD, they can log in using a partner's AD, they can log in using a GitHub OAuth credentials if they want, or they can use their custom email and password that I have saved in my SQL database. And you can do all that with that provider. And like I said, Identity Server is a good solution for that. It's a free open source tool. You have to configure it, right? So it's not like it just works out of the box, but it does implement all these protocols for you, and you just have to add your special rules on top of it. All right, so the next thing you might do that gets you away from vendor lock-in is consider using containers. And so if you use containers, you can still host everything on Azure, but now you could also host it on your cloud provider of choice because all of them support Docker containers. And so now your client machine can come in and it can authenticate with the identity system, get a token, and then make requests to the different applications providing that token and have access to whatever resources they're trying to get to. The other thing that is nice about this layout here is that notice that each one of the applications now has its own set of resources, its own Redis cache, its own Azure SQL, and those containers individually can be scaled up if they need to be. So instead of having to scale up the whole app instance, now you can just take whatever's in the container and scale that up. All right. Yeah, and somebody mentioned Azure AD B2C. I have not actually used Azure AD B2C, but it is also another option that you should think of. And Mark, yeah, Okta was the one I was thinking of. So yeah, Okta's another auth provider. Auth0 and Okta are the two biggest third-party providers I know of, and probably Azure AD B2C for that matter. That's just a mouthful though. It's AD B2C, like you get the first 4 letters of the alphabet right in there. It's a mess. Okay. All right, so now that we're talking about containers, we'll just throw this up there in case you haven't seen it before. I'll have another quick sip of water. All right, so Kubernetes. That's all I'm going to say about Kubernetes because it's outside the scope of this talk. But if you were using Kubernetes, that would be something that could help you scale up those containers that you're using in the previous slide. Okay, so let's talk about data sync for a second. Every one of those apps that we just showed, back up here, has its own data, which sounds beautiful. And the domain-driven design person in me just loves it because now each one of those has a nice, beautiful bounded context around it. I don't have to worry about anybody else stepping on my design. If I want to change my model of the problem, I can change it in the code, and I can change it in the database. All the way through my whole application. My ubiquitous language can use whatever new term I just came up with. And that morning I sat down with the customer, we realized that we'd modeled it wrong. We changed it, I checked in the code, and an hour later, the entire application is running using that new understanding of that model, that new language. That's impossible to do with a shared database where everybody's using the same set of tables for things, and you're constantly trying to put square pegs in the round holes because that's what you've got to work with. Okay, but these applications probably aren't totally isolated from one another, right? It's possible that application A is like the guest registration system, and application B is a billing system. And when the user comes in and they registers in application A and they provide their address, so that you can send them a bill or send them a note. Application B wants to know what that address is. And so how do we get data between them? Because we don't have a central database now that's going to act as our single place to integrate all the data changes. And that's where data sync comes in. And the most common approach is to implement some kind of message or event bus. And so we would have these different systems here, like we've just laid out. And on the backside, we would have some messaging. We'd have some event bus occurring. And what you would do is you would have each app publish events whenever certain updates occur. So in app A, when a new user registers or when they update their address, there would be an event that would publish on the bus that would say, customer updated address event. And app B cares about that. App B has a copy of the customer's address that it keeps just for this reason. And whenever it sees an update message come by on the bus, it takes that message and it acts upon it and it says, oh, now they're at 123 Main Street. Let me update my copy of that data. App C doesn't care about the address. It just lets that message go by. It doesn't care. It maybe cares about other messages, right? But each app can decide which types of messages it wants to deal with. Now, that means that there's going to be some eventual consistency here, hopefully, where app A makes some change, and for some period of time, app B doesn't see it. So it's possible that a user that's interacting with both of these apps, or two different users interacting with both apps, may see different things at the same time. So even after the user updated their address in app A, it doesn't appear as updated in app B for some period of time. Usually that period of time is going to be very short. It could be milliseconds, could be a couple of seconds. Sometimes it could be very long if bad things happen, right? What if the event bus falls over? What if app B is down for maintenance and a whole lot of messages have queued up? And so when it comes back up, it needs to chew through all those events to do something with them before it gets to that update that it needs to know about. There's scenarios where data consistency can be an issue. What you might be tempted to do is to have each app talk directly to the other apps about what they need or when they make updates, right? Instead of using a bus, maybe app B exposes an API endpoint that says update address. And whenever app A updates their address, as part of that task, they call app B's HTTP endpoint and say, hey, update this customer's address. The problem with that is that it doesn't scale well, and it's horrific for your uptime, because now any request to app A only succeeds if app B is up at the same time. And you can imagine as you go from 2 or 3 up to a dozen or more different processes that all need to talk to one another, that gets worse and worse and worse. So you're never going to get very many nines of uptime if every request is now this spider web of requests across all your applications that all have to be up. By using an event bus, we can make updates to app A, and app B and app C could be totally down at that time. App A does its job, finishes up, returns back to the user. The user doesn't know anything's different. And eventually, when app B and C come back up, they will get caught up and they'll get back up to speed, right? So it decouples the apps from one another in terms of this temporal coupling, where they no longer have to be up at the same time. As long as they're up at some point and the message bus is resilient, which it should be, then they're going to get caught up once they are back up and running. All right. The other thing that we should talk about here is microservices that goes, along with cloud apps. The idea with microservices is that instead of having apps, which are these very coarse-grained things that you deploy and scale as like large sets of features, you want to take some common functionality that's duplicated between apps and pull that out into a separate part of the system. It's its own standalone application, essentially. If you have these large coarse-grained apps, one thing that happens is there might be parts of that app that are very stable, that aren't changing, that nobody's adding features to. But those stable parts are disrupted by the unstable bits, right? Every time you need to make a deployment to the app because you're working on this new feature over in this one corner of the application, there's a chance you're breaking all the rest of the app. And it's likely that you're bringing the whole app down whenever you deploy, depending on how you do your deployments. So one of the benefits of microservices is not just for scalability, which is what everybody talks about, but also in order to just add some resiliency, in order to say, these parts of the app are done. they're not changing. We're not deploying them. We almost never change them. Why don't we just deploy those as a separate microservice and never touch it again, right? And now all the new work can happen in the app or in some other service or whatever. But those things that you deployed as microservices individually that were stable can just sit there and continue to work day in and day out and never get impacted by another deployment. So it can be good to decompose your apps into small, independent, cohesive microservices. It's not the go-to pattern that you should always assume you're going to get to, though. It's often got more costs than it's worth. So be very careful before you decide microservices is an obvious design decision that you want to take. All right, now here's an example of an e-commerce site. This is the eShop on Web site that I maintain for Microsoft on GitHub. And as it stands, the eShop on Web site is just a monolithic application. It's an ASP.NET Core app. Everything deploys as one web project. The architecture consists of like 6 or 7 projects, 3 production ones and 3 test ones, and I think a Docker project. So it's pretty small, right? You can open the solution, it's not a huge thing. There is also another GitHub repo called eShop on Containers, and it is a reference architecture for the exact same app, the same online store, but using containers and Kubernetes and microservices. And as you'll see in a moment, it is way more complicated. And you can see how it kind of breaks all these things up. I tweeted about this recently. I didn't come up with this cartoon, but I think I saw it on Slack somewhere, and I thought it was great, so I tweeted it, and it got like over 1,000 likes on my Twitter, which was great. So, but I totally agree with the message here, which is that your microservices architecture is not necessary most of the time. Like, I'm really happy that I'm maintaining the eShop on Web monolithic reference app for Microsoft and not the eShop on Containers one. Even though the eShop on Containers one has 10 times as many stars on GitHub, because developers really just love complexity and want to see that stuff. So yeah, all the developers are like the natives here responding to this alien. All right. So you can split things up into microservices. You could take your client app and you could split it up into different calls for each client if you want. You can have multiple different things that the different microservices handle. It's not unusual to have identity as a microservice, for example. There's a bunch of different patterns you can use with microservices, which we're going to talk about in just a second. So in this scenario, if you have a few different services that each correlate to some part of an application, maybe this app has things like a catalog, a shopping cart, a checkout or payment provider, things like that. Those could be your 3 services here, right? So when the client wants to call to these different microservices that you've rolled out, the client has to know about all the different ways those microservices do things. And ideally, your microservices are independent from one another, developed potentially by different teams or different sets of devs. And so they may have very different assumptions about how they work. They may not all be 100% consistent. There may be some overlap about how they do things. And so the client developer now has to know about each of the different microservices, what their different rules are for how they do things, because they probably aren't 100% consistent. They have to be able to authenticate with each one independently, right? Hopefully there's one identity server token that they can use and present it to each microservice, and it'll work for all of them. But when it expires, it might expire for one before it expires for another, or there could be other reasons why it stops working for one instead of another. So there's issues with having a client have to know about many microservices. All right, so there's security concerns. One thing might be the surface area that's exposed. If you have these sets of microservices, each one exposes, let's say, 10 API endpoints. So between those 3, you've got 30 different API endpoints. This store might not need all of those, or maybe the mobile app doesn't need as many as the web app does, right? And so it has a smaller surface area that it needs. The more features you expose, the more possibility there is for a security problem. Your microservices might have a bunch of different clients, and they might have different things they need. The security rules for one may not apply to the others. And in general, it's just a good security practice to limit surface area to just provide what the client needs. And so that brings us to our next cloud pattern, which is the API gateway pattern. And so you can create an API gateway. You can deploy it yourself as just a container. There's open source tools like Ocelot that you can use for this. There's actually an example of using Ocelot in the eShop on Containers sample. And you configure the rules for how this gateway is going to work, which endpoints it's going to expose, how it's going to route those to the backend microservices. And you can think of this gateway as kind of like a load balancer / router / firewall for your microservices, right? It kind of stands in between and proxies requests to them, but also you configure it to say what gets exposed. Okay, so you can talk to this API gateway from the clients. From over here, you can have your mobile app talk directly to it, your web app running Angular, JavaScript, or Blazor, WebAssembly, whatever, talk over HTTP to it. You could also have a traditional web app where all the client stuff is done on the server using like old school web forms or ASP.NET MVC. And so then the server itself could talk to the API gateway instead of going over the internet. It would just be inside your data center at that point. Okay. All right, so the app gateway pattern is nice. There's actually an Azure tool that you can use for that. It's Azure API Management. It's got the gateway. It also has a portal for publishers and for developers. Developer portal basically lets you configure all the rules and how they work and who can do what. And then the publisher portal provides the documentation for what's, how to work with the APIs that are exposed. All right. Another common enough pattern that it's worth talking about is how to access secure files. So let's say you've got this app, and now one of the things you want to be able to do is let users download these PDFs or these videos, and you want to make sure that users can only get to their PDFs and their videos, or the ones that have been shared with them, right? Something like what Dropbox does or OneDrive or something like that. So what you don't want to do is just store all the videos or whatever, all the files in blob storage in the clear with no authentication, and then just check to see if the user's authenticated, and if they are, do a 301 redirect to the resource they need, right? Because as soon as they get that redirect, now they can see in their network tab what the URL was. And they can take that URL, they can paste it to the world, throw it up on Twitter, and now anybody can get to that resource. It's not really secure just because you put it out there in a hard to guess CDN blob storage URL. All right. So you have some app that needs to control these media files based on who the user is. Just using a dumb CDN that doesn't protect the actual URLs doesn't work. So your current solution is that your web app is going to authenticate the user, and then inside the back end, the web app is going to go access the file and then stream it down to the end user. Now the downside to that is bandwidth and performance, because now you're going to be locking up a thread and chewing up a lot of bandwidth to do that, right? The client machine is going to make a request, and then you're going to go get it from blob storage, and you're going to pull it back through your web app and then send it back to the client machine. Concerns here is the load on the web app is much higher than necessary, and the cost may be prohibitive because you might be paying both inbound and outbound bandwidth on those files twice because of this architecture. There's also a much greater chance of downtime with the web app and the file. Both are required in order to stream the file. So the next cloud-based pattern that you should know about if you ever run into this is called the valet key. And the way the valet key works is the user goes to the application and says, hey, I need to download this file. The application does not give them the actual file, but instead returns them a token, and that token can then be used to go and get the resource from the target store. So you provide direct access to the media file if they have an access token, then can then get to it. Azure has a thing called Shared Access Signatures, SAS, just like my initials, for this purpose. So if you're using Azure, this is what you would use. If you check the docs for this, it has all the exact code you need to set it up. So this looks maybe a little bit complicated, but it's pretty trivial to get set up. The nice thing about this is that the file transfers occur directly then between the client and the file store, but it's still secure, and the client can't just copy paste a URL to somebody else. All right, let me take another sip of water. All right, let's talk about remote resources for just a second. There's problems with remote resources that you want to talk to. And by remote resources, I mean anything that's not in memory in your application, right? So in your application, You would love it if you had fast, reliable, always on services, but get used to disappointment, right? It's just not going to happen. You're going to have other pieces of your system that just aren't always there. And so the next pattern that we're going to talk about is the retry pattern. So the retry pattern is pretty simple. We've probably all implemented it with a try catch block at some point where, your first attempt failed. So if it's likely to be a transient problem, then retry it. If it's not a transient problem, if it's like, your credentials are wrong and they're probably not going to be right again anytime soon, then just give up. So depending on the problem, maybe by inspecting the type of exception you got, you could determine this right here and decide whether or not you should just immediately give up or retry. It might seem like retrying is free, but it's not. It's got, costs associated with it, especially when you think about it at scale, right? If you have a whole lot of web applications that are all trying to hit the same remote resource and that remote resource blips for a second, and then all of them try and retry multiple times, right? You can denial of service attack yourself really quickly with that type of architecture. So assuming that you've ruled out that it's some other type of problem and you think that, yeah, maybe it'll come back up, you can immediately try again and then wait for a bit and then try again and then wait a little bit longer and then try again. And there's algorithms for this. We can do like exponential back off and things like that. Ethernet basically uses a pattern like this when there's collisions on the wire when it's trying to send things over the network. And eventually you'll just give up, right? It's like, sorry, this just didn't go through. We'll fail somehow. Now the problem with the retry pattern is that your retries can overload the downstream service. Imagine your typical load is 10 requests per second, and you try a typical try 3 times and then fail strategy. So when the service comes up, it is immediately seeing 30 requests per second of load because of those requests, all hammering it right away. This can result in longer time to respond and creation of more resources than necessary because if you have some elastic scale in place and it's looking at how many requests are queued up or what the CPU load is on the service, it sees the service come back up and immediately, the CPU load is pegged, the services are queuing up and backing up. It's going to start spinning up new services because it thinks it has to because of all that latent demand. But then within a few seconds or maybe a minute, things should be back to normal and everything should be fine, right? And all those retries, they weren't real requests because they were just pent up requests from previous things that were going on. So there was probably no need to queue up additional resources in most cases, but that can have an impact on your cost when you do that. So don't DOS yourself with these retries, which leads to another pattern, which is sort of like an evolution of the retry pattern, and that is the circuit breaker pattern. And the circuit breaker pattern is generally going to have 3 states, right? There's closed, which means working. And it seems counterintuitive to me, even though I've taken electrical engineering classes. Closed for a circuit is good, right? When the circuit is closed, that means all the electricity can flow through it. Things are working. When it's open, that means the circuit is not going to do anything, right? The circuit is broken and nothing can flow through it. It's totally the opposite of everything else that's open or closed, right? If you're going to go to the store, when it's open, you can go in and you can use it. When it's closed, you can't, right? This is the exact opposite of that. And it has an interesting third state, which is called half open or throttled. And so these states look like this. In the closed state, everything is working, right? The system expects that remote resource is available. It's making requests to it. Requests are being handled and coming back. Everything is fine. But there is a fail count that is being kept, right, for a certain amount of time. And so the fail count is currently set to 0. Everything's great. But something bad starts to happen, right? The remote resource goes down. Now the fail count gets incremented, right? And there's a retry, right? So something didn't work, increment the fail counter, retry. Increment it again, retry. Okay, once the fail count exceeds a certain threshold, we're going to open the circuit breaker. So the circuit breaker now, when it's open, means that no more requests are going to hit the third-party service. All right, so it just sits there open. Any requests that are coming through are either just in a waiting state, they're not retrying, they're just waiting, or they're just immediately bypassing that request, right? They're throwing an exception, whatever they're doing, they know the circuit is in an open state and they're not going to make any calls to it. After a certain timeout, then it moves to a half open state. And a half open state is where some requests can actually go through. Not all of them, right? But it'll just be a very limited throttled request. So, every second or so, one request will try and hit the service to see if it's still there. If it's still not responding, then it goes back to open and it waits for the timeout again. And then half open occurs again, makes a request, still doesn't work, goes back to open, repeat until eventually these requests start to work. When the requests start to work, then we're going to switch from half open to fully closed. I wanted to say fully open, but it's again backwards. You switch over to closed, and that means that the system's all back to normal again, right? The failure count's been reset to 0, and the system moves on as if everything were happy. Now, you could implement retry logic and circuit breaker logic and stuff yourself, but there is a third-party tool called Poly. I don't know if very many of you have used Poly, but it's a .NET resilience library that you can get off of NuGet, and it will handle a lot of these policies for you. So it does circuit breaker, it does retry, handles timeouts, and a number of other things in a fluent and thread-safe manner, and it works with .NET as well as .NET Core. So check that out. All right, there's those. Okay, so let's do one last microservice anti-pattern here, which is how we do reporting. And so this is from the Microservices Anti-Patterns and Pitfalls book by Mark Richards. There's a link there at the bottom. And so he demonstrates a few different ways that you can do reporting. And so most business systems, they have some need for reporting. And it's sort of separate from how they do the application, right? Which it should be, right? Reporting is a different use case than the transactional nature of a lot of our applications. And so if you're using microservices and you really are doing microservices where they have their own database, then this first approach is to use what's called reach-in reporting, where you have a separate reporting service and it needs to know what's going on, so it just makes calls directly to those individual microservice databases to get the data it needs. The problem with this is that now those microservices no longer own their data, right? Now they have all the same problems they would have if there were a central database, because there is this reporting service that is depending on that data. And if the blue microservice today decides they want to change the table names for something, as soon as the reports start to run, they're all going to be broken because they're expecting the old table names, and things are bad. So it introduces coupling, reduces independence of the microservices, bypasses microservice logic if that matters. And so there's reasons why you don't want to just directly go to the database. Okay, so that's cool. We'll just create some new endpoints for the reporting service to use, and we'll expose those from the microservice, and we'll lock them down so that only the reporting service can get to them, and it'll look something like this. All right, so now we're not going to bypass the microservice. We're not going to know about the database structure directly. The problem with this is that the performance is usually horrid. Reporting services work really well when they hit relational databases. They don't work really well when they have to hit HTTP endpoints. The data itself might be too large. It might be difficult to perform complex queries. There's just all kinds of pain that usually comes from trying to do this approach. Okay, so number 3, your third approach is, well, let's just have a batch job that updates the reporting database from the microservice database. And so it kind of decouples the reporting service from direct access. And now the reporting service, like the biggest difference here is the reporting service has its own data store. So in this first one, this is approach 1, the service just directly hits the data and creates the reports. This third one, now we've created a separate database just for reporting, right? A data cube or something like that. And we have some batch thing that's going to go grab stuff out of our transactional databases, store it in the reporting database, and the reporting service just talks to that. This is okay, except it has the same coupling problems as the first approach, right? We're still directly reaching into the databases. So we don't want that. So this third approach is probably the best one that you want to think about. And so the idea here is that the microservices, in addition to all the other things they're doing, they will publish events whenever they make changes to the data that the reporting service cares about. Not necessarily all the data, because there's lots of data in the microservice database that probably nobody else cares about. But if it's data that you care about for reporting purposes, then you will publish events that say this was updated, this was inserted, this was deleted, and those events will go onto some event bus. And just like that same event bus architecture that we're using to keep the microservices in sync with one another, we will use that same architecture for the reporting service. Now, there's still going to have to be some separate data capture service listening for those events and making updates to the reporting database, but we've eliminated all of the coupling concerns that we had before. All right, any questions about that approach versus the other two possible approaches for reporting purposes? All right. That is most of what I wanted to get through today, actually, so that's good. Our key takeaways: using cloud architecture abstracts away from the servers. The cache aside pattern works really well for performance. Containers can give you some better deployment and scalability options, and they help reduce vendor lock-in. Microservices can be a good way to get fine control over a certain part of app functionality, either because it needs to scale independently or because you just want it to be stable and not have to touch it again. And you don't want it to get broken by other things that get updated. Federated identity makes a lot of sense as soon as you start to have multiple applications that need single sign-on, and especially if you're going to have multiple different ways to authenticate users, whether that's AD or third-party OAuth or your own built-in user records. Federated identity is great for all that. If you're going to have multiple different microservices and you're going to have multiple different clients that need to talk to them, API gateways make a lot of sense. There's a related pattern I didn't mention called BFFs, or backends for front ends. And what that basically means is each front end that you're going to ship, each client, each mobile app, each spa, whatever it is, you're going to have a separate back end for. And the API gateway is an easy way to implement this, so that it only sees the surface area of APIs that it needs, and it doesn't need anything else. So that's another related pattern, like a bonus. We also have valet key, which we talked about for getting access to like large secure media instead of having to stream it through your app itself. We talked about using retry as well as circuit breaker, which you can get for free more or less with Poly as a library for work with .NET. And we talked about the reach-in reporting anti-pattern that you want to avoid in your microservices when you're using those. There is actually a whole book on cloud design patterns that has most, if not all of these covered in it, that you can get here from this URL. This is actually available online. It's a free book, and it's a PDF, and it's also online on Microsoft Docs. So if you just do like a Google search for Microsoft Cloud Design Patterns, you'll probably find it. My book on cloud native apps is available here. Same deal. It's also available online on Docs. So if you just search for the title, you'll find it on Microsoft Docs page. You can get it as a PDF, or you can just read it in your browser. And there's all my info that I covered today. So I am happy to hang out and answer questions and discuss.
Excellent. Thanks, Steve. Does anyone have any questions for Steve? I see one comment in chat. Just a thank you. I got one question for you. Have you ever been to a client site where you saw microservices running and you recommended against it? And if so, what was that scenario?
I've never got into one where they had it all working already, and then I said, "Hey, rip that out." They're still new enough that most of the times when I'm coming in, clients are trying to implement them. But I do always caution them that it shouldn't be your first thing that you go to. I would always build and design the monolithic app first, and then split off the microservices after. And I have seen numerous instances where companies have tried to do microservices up front for some big application they were building and spin their tires and just waste a lot of time trying to get all that working before they really understood what they were building. Right. And so I think it's much easier to ship something faster if you're building a monolith. And then once you've built it and you know what it is, and you build it, with tests and with clean code and all the things that you want to use to make it so it's easy to change later, those principles and patterns that you follow will make it easier for you to split pieces of it off into their own microservices. So I
Gotcha.
think the quick answer to your question is no.
Gotcha. Okay. Thanks. Any other questions for Steve?
Dave has a question about events. Go for it. They can
You
unmute
can come off
themselves,
mute,
right?
Dave.
Sorry, can you see me? There I
I
am.
can hear you fine.
Okay. I was wondering about given a monolith, that is in somewhat DDD style, right? But we don't have events in place yet. We add some events. So given a bus, right? If we wanted to just like split this thing in half and make side A talk to side B, how does dealing, I don't know, how splitting the app across like that in terms of domain events, is that really a one-to-one type of concept, or where does that sit in like the Blue Book's mind map?
Domain events aren't necessarily the same as cross-application events, which are often called integration events because they have to do with how you integrate between two different applications. I would generally kick off events using domain events in a system, but not every domain event would correspond to an integration event, and what they look like is going to be different. So, as a quick example, let's say my DDD fundamentals course was a veterinary clinic, and it had an appointment scheduler. And so when we changed an appointment, we would have an appointment updated event that would fire off. And within the domain, things cared about that, right? They would go and they would update the UI, and we would run validation logic, and we would update the schedule, and the schedule would check and see if there were conflicts. And the only thing we needed to pass around on that event was the appointment ID, because inside of our domain, we can easily convert from an appointment ID into an actual appointment anytime we want because it's in our domain. But if I wanted to fire that off to some other system, for instance, using that same example, when you created a new appointment, it had a separate event, was a appointment scheduled event, I think. And so one of the things that happened when you scheduled an appointment is it would fire off an event that would go to another application, in this case, the public web app, and it would send an email confirmation to you and say, hey, confirm that this is your appointment. Now we wouldn't, as that integration event, we wouldn't just send the appointment ID, right? Because now that other system doesn't have the information it needs to be able to send an email and tell you to confirm it, right? They're immediately going to have to call back to us and hit our API and say, give me whatever details I need about appointment ID, 123. And so one of the things that you will see when you're dealing with this scenario is you might have a domain event gets raised, a handler in the domain for that domain event whose only job is to hydrate that event, to denormalize that event with additional stuff that it needs to send it over the wire, right? Because domain events just happen in memory inside your app. These integration events actually go over the wire somehow, right? They go to a message bus, a message queue, a database, something. And so it might put in additional stuff that might be interesting. So in this case, to send an email, which I know is what is needed, they're going to need to know the person's name, the pet's name, the appointment date, which doctor they're seeing, whatever. I'm going to stuff all that into this appointment confirmation event that goes over the wire so that this other system that wants to send the email can pick that up, get all the data they need right there, and be able to send that email. So I don't know if that totally answered your question, but it is something to think about. It's like, yes, domain events are part of it, but don't think that there's totally a one-to-one correspondence. Like every domain event doesn't now have to be on the message bus. They should still just be in memory, but you should be able to pick and choose the events that you want to have as integration points with your other system. And then you want to have a place where you translate between a domain event and an integration event.
Yeah, no, that's a good way to think about it. I hadn't thought about that. So, I'm planning for application events and domain-specific events, but I guess thinking about this third category is definitely giving me food for thought. Thank you.
Sure.
One other question, Steve. If you look over in the chat window, Pam has a question.
I'm actually looking for that type of thing myself, as far as where is best to store like small videos. Um, like that Dev Better thing that I mentioned has a whole host of videos, recordings of our previous Q&A sessions and stuff. And like right now, I'm storing those in my Dropbox. Right, and it's basically free because I'm already paying for it. I don't recommend that for any bigger things, but I'm looking at other options. Right, Azure Blob Storage is not great for that. Azure Media Services is another one I've looked at. Office 365 has support for video storage as well that you can stream. You can use YouTube and mark things as private or unlisted, and it has an API. I have not considered using Google other than YouTube, right? I mean, they own YouTube, but I don't know about a Google offering for that. The one that I'm considering moving to is Vimeo, actually, because Vimeo has a pretty decent pricing and features. So I may go there. It wasn't too terribly expensive for what I was needing. It really comes down to what you need though, like how many videos do you have? How big are they? Is it? Okay. Yeah, Pam's saying it's very expensive compared to Microsoft Blob. It might be like Microsoft Blob I had to rule out because I can't use any of the video controls with it. There's no way to stream it. There's no way to have a nice player experience where it buffers. There's no way to provide a URL that just goes to like go to this video and start it at second 120, right? Like because like at 120 seconds in, that's where we talk about this thing, right? And I want to have that as a URL that I can bookmark. It didn't support any of those features, so I had to rule it out. And Vimeo wasn't terribly expensive compared to Azure Media Services and Office 365 and some of the other things that I'd looked at. So depending on what you're doing, there's also tools that are actually like whole LMS sites, like learning management platforms. Thinkific is one that I've used in the past, and it will host your videos for you. Yeah, I don't. If you have a URL for where it is in Google, let me know because I don't know. I don't even know where to look for Google, whatever. What product is it that Google has? It's not just Google Videos, right? It's not YouTube. But I would check it out. I would be happy to look at it because I haven't found a good scenario, a good solution for my scenario yet. I'm not sure what is a third party. Okay, yeah. I don't know if I answered your question. Hopefully I did. As you can see, I'm still struggling with that myself. So my Dropbox solution works-ish, but it doesn't give me the nice player experience either. But it doesn't cost me anything, so there's that. Okay, yeah, sure thing.
Okay.
My email's right on the slide.
All right. Thank you very much, Steve. Appreciate it.
Thanks.